Welcome back to the deep dive. When we think about certain systems, failure just isn't an option. I'm talking about the software in an ICU or high-frequency trading platform or even the AI guiding a power grid. In those spots, relying on a single server, no matter how powerful it is just it's just asking for trouble. It's fundamentally brittle.
It is, and the problem today is that faults in these intelligent systems, they can propagate almost instantly. They move much, much faster than any human operator could possibly see, diagnose, and then react to. That speed difference is really what makes the old ways of thinking about redundancy, not quite enough anymore.
Right. And our mission for this deep dive is to get into an architectural solution built specifically to beat that speed problem.
Yeah.
It's called the Resilient System Framework, or RSF. And this isn't just about having a backup server sitting in a rack somewhere. It's a really meticulous, layered approach to high availability. And this is the key controlled recovery. But here's the twist, the thing that really caught our attention. We're going to unpack why the way most engineers would instinctively calculate the reliability of a system like this is just wrong, fundamentally flawed. And we'll see how fixing the math actually reveals the real secret to its resilience.
It's an elegant framework because it really does attack multiple failure points at once. It forces you to have active redundancy, very strict checkpointing to keep things in sync, and then these layers of automated validation, and finally, a human supervisory layer that you just can't bypass. It's a whole ecosystem built to take a hit and just keep going.
Okay, so let's unpack that core architecture layer by layer. The RSF has 4 distinct layers, and you can almost think of it like a defense in depth strategy.
Yeah.
Everyone has a very specific job.
Exactly. And the first 2 layers, L1 and L2, they're all about the core function, the actual computation.
Okay, start us off with L1.
So L1 is the active processing unit, the APU. This is your engine room. It's the primary system doing all the real-time work, serving the output, talking to the world. It's the component that's, running the show right now.
And L2 is its shadow, right? Always there.
That's the mirrored backup unit, or MBU. This is your standby node, and its whole job is to stay in perfect sync with the APU through constant state updates, checkpoints. Its only purpose is to be ready for an instant takeover. If the APU stumbles, the MBU has to step in and become L1 immediately with 0 data loss.
Okay, so L1 and L2 are the muscle. They're doing the work.
Yeah.
But a system needs more than just power. It needs awareness. Which brings us to L3.
L3 is the Anomaly Detection System, the ADS. This is your automated watchtower. It isn't running the main job, but it's constantly watching the outputs and the internal health of L1 and L2. It's looking for anything: performance degradation, weird data drift, silent failures. And the moment L3 spots something, it doesn't just ring an alarm, it triggers a pre-planned automated response.
So it's the trigger and the first responder all in one.
You got it. And that leaves the final layer of command, L4.
The human element.
L4 is Human Supervisory Control, or HSC. This is the ultimate governance layer. It provides the approval gates for really risky actions. It's the manual intervention point when the L3 automation just isn't enough. And, maybe most importantly, it provides a controlled way to roll things back. It ensures that even with all this automation, a human has to sign off on the big stuff, like deploying a huge update.
It's so clear when you lay it out like that. Building a system with these 4 layers, it just fundamentally changes what uptime even means. It's not just about not crashing, it's about managing failure gracefully. You get the obvious benefit of removing single points of failure, sure, but you also get this incredibly fast, validated recovery.
And to really get it, you have to see how these layers dance together. The framework defines 3 main operational modes that dictate that interaction.
Okay, let's start with the baseline, the day-to-day, normal mode.
In normal mode, everything's humming along. The APU is active. The MBU is just quietly syncing in the background, getting its state checkpointed every few milliseconds. The ADS is running its loops, checking data, and the HSC layer is, well, it's passively governing. It's on standby, holding the keys for any big changes.
Eventually something breaks. So how does the system flip into recovery mode?
Recovery mode is triggered by L3, the ADS, detecting a critical fault in L1. The first priority is just continuity, so the service fails over to the MBU, to L2 as fast as possible. Now, while L2 is keeping the lights on, L1 is taken offline, it's isolated, and diagnostics are run. And critically, the ADS is also verifying the integrity of that recovery. It's making sure the state that L2 took over was clean.
Right, you don't want to fail over to a corrupted state. That would be even worse.
Precisely.
And then there's the other big moment of risk for any system, updates. How does update mode work?
Oh, absolutely. Updates are probably the most dangerous time. The RSF handles them so carefully. An update isn't just pushed live, it's staged and validated first. The MBU acts as the continuity buffer, so there's no service interruption. The update gets deployed to the offline APU to L1, then the ADS, L3, just hammers it with regression checks using production-like prefix. And only after all those automated checks pass does L4, the human governance layer, get the prompt to approve promoting that new code into production.
That systematic approach really explains why this framework is so important right now. This isn't just some, academic exercise.
Not at all. It's extremely practical. We see this kind of thinking anywhere, that real-time integrity and zero downtime are just non-negotiable. Think about AI services making critical decisions. You can't have your fraud model go offline.
Yeah.
Or healthcare data pipelines, financial transaction systems, even infrastructure monitoring where a missed alert could mean physical danger.
Okay, so we've got the architecture, the players, the playbook. Now let's get to the heart of it, the math. Because for any systems engineer, for any stakeholder really, quantifying reliability is everything.
And this is where we find that core mistake in how people first model the RSF. When they first see those 4 layers, APU, MBU, ADS, HSC, their gut tells them to treat it as a symbol series system.
Like a string of old Christmas lights, right? Where if any single bulb goes out, the whole string goes dark.
That's the perfect analogy. So the initial very tempting but very flawed math is just a product. You'd say system reliability equals reliability of the APU times MBU times ADS times HSC.
And if you use that math, you're actually punishing the system for having these extra safety nets. If your anomaly detection system is, say, only 95% reliable, that broken math tells you your entire system can never be better than 95%, even if your core processors are perfect.
Exactly. That's the conceptual mistake. The entire point of the RSF is to defy that series logic. L1 and L2 are fundamentally parallel and redundant. The APU failing isn't a system failure, it's a planned event that triggers a transition. And likewise, L3 and L4, the ADS and HSC, they aren't components that need to be up for the system to work moment to moment. They are mitigation and coverage layers that only act when something goes wrong.
Okay, that completely reframes it. We can't just measure simple uptime. We have to measure the quality of the safety net itself.
That's the insight. So the better model, the correct model, splits the system into 2 factors that work together. You have your core compute layer reliability, let's call it R compute, and then you have your mitigation coverage, C mitigation.
Let's start with R compute, the L1 and L2 pairing. In a standby system, it's not just about them being up, it's about the switch between them.
Yeah. That switch is everything. We have to introduce a term for it, failover coverage, or JAMA. Gamma is the actual measurable probability that when the APU fails, the failover process itself works and successfully transitions service to a healthy MBU. If your gamma is low, your redundancy is just an illusion.
I see.
So our R compute has to reflect that. It's the probability that, 1, the APU just never fails, or 2, the APU does fail, but the failover works. That's gamma, and the MBU is alive and ready to take over. It's a more complex formula, but it captures the true value of that standby unit.
Okay, so R compute handles the hardware continuity. Now, what about the intelligence layers, L3 and L4? How do we model them as a measurable safety net, that C mitigation?
We treat C mitigation as the probability that if a fault happens, it gets caught and fixed before it becomes a catastrophe. It's like quantifying the reliability of your car's automated emergency braking, which is then backed up by you, the driver, slamming on the brakes.
Okay, so it's a sequence of events.
A sequence of 3 measurable probabilities. First, you have delta. That's the detection probability. It's L3's job. What's the probability that the ADS even sees the fault in time? If delta is low, nothing else matters.
Okay, so if L3 detects it, then the automation kicks in.
Correct. That's our second term, alpha, the automated remediation success probability. This is the chance that L3's pre-programmed response, like a quick restart or a rollback, actually fixes the problem without a human needing to get involved.
And if that fails?
Then we have our last line of defense, L4. That's beta, the human intervention success probability. It's the probability that when automation fails, the human supervisor can step in and correctly contain the fault.
So it's a clear chain, detection by delta, then an automated fix by alpha, and if that doesn't work, a manual fix by beta. The overall mitigation coverage, C mitigation, is the chance you succeed at detection and then succeed with either the automation or the human backup.
Exactly. This model makes governance and detection into what they are, explicit risk reduction functions. They aren't just another link in a chain to fail.
So we bring it all together. The final defensible model is that the total system reliability is approximately R compute multiplied by C mitigation. Wow. That completely changes where you'd focus your engineering efforts. It's not just about buying better hardware anymore.
It changes the entire conversation. You stop asking, is my server up? And you start asking, how effective is my failover? And what's the probability my detection system misses a subtle data corruption?
Which brings up a huge practical question. If we're going to rely on these coverage parameters, gamma, delta, alpha, beta, we can't just make them up, right? We
Yeah.
can't just assume they're 99.9%. That seems incredibly dangerous.
It is. It's the fast track to catastrophic overconfidence. They must be derived empirically, period. There's no other safe way. You need telemetry, you need rigorous post-incident reviews, and most importantly, you need controlled fault injection exercises, what some people call chaos engineering.
Okay, let's talk about the hardest one. How on earth do you measure delta, the detection probability, without waiting for a real disaster?
You create tiny, controlled disasters. You use synthetic anomaly injection. Engineers will intentionally, under very controlled conditions, feed the system subtle, broken, or weird data, and then check two things. One, did the ADS actually flag it? And two, did it do so fast enough? The more complex the system, the more creative you have to be with your fake problems.
And what about that critical failover coverage, gamma? Do you just turn off the main server and hope for the best?
In a controlled way, yes, you have to. Gamma is measured by doing periodic takeover drills. You simulate an L1 failure cut its network, kill the power, and you record how consistently L2 takes over within your required time. If you run 10 drills and the takeover only works cleanly 8 times, well, you have a measured gamma of 0.8. And you have to use that number in your model, not the 0.999 you wished for.
So constant rigorous testing is the only way to make the math real.
Yeah.
But you mentioned there's a limitation, a kind of kryptonite that can wipe out all the benefits of that L1, L2 redundancy in an instant.
That's the ever-present danger of common cause failures. Redundancy is only real if the two components can fail independently. If they share a dependency and that dependency fails, they both go down together.
What's a classic example of that?
The most common one today is probably a shared software update. If you push a new piece of code with a subtle bug to both your primary APU and your backup MBU, that one bad update can take them both down at the exact same time. Your redundancy is gone. Another example would be relying on a single cloud vendor's region or a shared power supply.
And if you don't model that shared risk, you're lying to yourself about how resilient you are.
You are vastly overstating it. To do this right, you have to add terms to your model, like a common cause failure rate, to force engineers to acknowledge and design around those shared dependencies.
Now, what about when things get insanely complex? Not just 2 servers, but dozens of microservices, maybe some managed by AI. Do these models still hold up?
They can start to feel a bit inadequate. For systems where uncertainty is really high and the dependencies are messy and nonlinear, the best tool is often something called a Bayesian network.
How would that work for the RSF?
A Bayesian network is like a probabilistic map of your system. You model the APU, MBU, ADS, and so on, not as simple percentages, but as nodes with conditional dependencies. For example, the probability of the MBU failing might be dependent on whether the ADS detected a network problem before the MBU's sync check failed. It can handle that kind of complex relationship. And the huge benefit of a Bayesian network is that it can learn, it can update. As you collect more real-world data from telemetry or from those fault injection tests, the network constantly refines the probabilities in real time. It formalizes that measurement loop we were talking about.
This has been an incredibly thorough deep dive. We've gone from a simple idea of a backup to a rigorous, defensible framework for true resilience. And I think the key takeaway for you, the learner, is this. Real high availability does not come from just buying a second piece of hardware. The strength of the resilient system framework and the honesty of its math comes from measuring the quality of its safety layers. That detection probability, delta, the automation success, alpha, the human intervention, beta. The call to action is to stop just measuring uptime and start measuring the quality of your recovery.
And that actually leads to our final provocative thought. The RSF is designed for maximum reliability, and it achieves that through tight governance, especially that L4 human supervisory control. But if you make a system maximally safe through human governance, you are, by definition, putting constraints on its behavior. So this raises a question. As our AI systems become more and more autonomous, how much of their potential for advanced, emergent, open-ended functionality is being stifled by the very safety mechanisms we put in place? What's the real trade-off between absolute resilience and complete, unconstrained autonomy? Something for you to chew on until next time.